I don't know what stuff is made out of, and I think I can probably convince you that you don't either. At the elementary school level, we learn that stuff is made of atoms, and later we learn that atoms are made of electrons, protons, and neutrons, and even later we might learn that protons and neutrons are made of quarks. And if you learn any quantum field theory, you'll learn that quarks and electrons are just different types of quantum fields. The trouble is, I don't know what a quantum field is, and I don't think anybody does. Now, your first guess might be that quantum fields are just descriptions of particles. You may have seen images like this from CERN, where it looks like there's particles traveling around, and these are things that are quarks and electrons and so on. But the notion of a quantum field representing a particle doesn't really work. And one way to see this is that the number of particles in a system depends on what reference frame you're viewing that system from. If particles are really the fundamental thing that describe reality, then they ought to not change depending on who's looking. This is a question of ontology, namely, we want to know the answer to what piece of the mathematical abstractions that describe quantum field theory correspond to physical things? What actually exists? So right from the get-go, it seems like the particle model is in high water. So what else could it be? Well, another possible option is that the fields are fundamental, and particles are just field excitations, something that would look like a picture like this. But the trouble with that is that it's not super clear what those fields actually are. But even this isn't super satisfying, because when we're talking about quantum fields, we're not talking about a number or a vector of numbers at every point in spacetime. We're talking about an operator at every point in spacetime, and the excitations are excitations in those operators, whatever that means. And if we want to ascribe some sort of physical realism to something, then it ought to be the case that it's not an operator, but some actual physical measurable property at every point in spacetime, and operators don't do that. Now, you could interpret this using the so-called VEV interpretation, where we describe data at every point in spacetime by evaluating so-called vacuum expectation values at every point in spacetime. We would need an infinite number of such things, but this would contain exactly as much data as the operators at those points in spacetime. And while in principle this does give actual physical measurable properties to every point in spacetime, it doesn't give us any sense of a physical field configuration. So in that case, it's not even super clear if the field is the physically real thing, or if it's just these VEVs, which are just measurable things. And then there's this interpretation called the wave functional interpretation, which is a lot like traditional quantum mechanics, in that you talk about the wave functional of your quantum field, describing a superposition of a bunch of classical field configurations. In some sense, that's the answer. We think of the quantum fields as being the physical things, and these are superpositions of classical fields. But in what sense can we talk about the properties of that field at a point in spacetime? After all, quantum fields are completely non-local things. They don't have well-defined properties at a place and time. It's really hard to say, because there's a lot of mathematical abstraction in quantum field theory and in quantum mechanics in general, and it's hard to say what's physically real or not. This is where things like the measurement problem come in. Perhaps it's best to just take quantum field theory at face value. The universe is a vector in a Hilbert space. But if we do that, it begs the question, what does it mean to physically exist? What really is real?